Hello everyone, myself Shubhajit. This is the first video in a series on stereochemistry. I am assuming that you know the basics like the meaning of enantiomer, diastereomer, etc. So, my aim will be to tell you some shortcuts or counting and transformation strategies that are helpful in solving questions. In this video, I am going to discuss how to interpret the Newman and Fischer projection formulas and identify enantiomer or diastereomer. Let me begin with the question. Here is the formal wording of the question. You can pause this video to give this question a try and then keep watching the video for the solution and also the concepts involved. Before proceeding with the solution, let me tell the concepts involved. The given compound has two chiral centers. First, we have to convert this Newman projection formula into Fischer projection formula. You might ask, why? An obvious reason is that the options are given in Fischer projection formula. But there is one more reason to do this. Whenever we convert Newman projection formula into Fischer projection formula, there is one data that we are ignoring, that is the torsional angle or the dihedral angle. Differences in torsional angles results in conformational isomers. It turns out that to reduce the complexity of the problems, we ignore the conformers. Generally, whenever questions ask to calculate stereoisomers or compare two stereoisomers as enantiomers or diastereomers, it is implied that they are talking about configurational isomers and not conformational isomers. Okay, returning back to our problem. There is a popular phrase, Fischer is an eclipsed Newman. So, we are going to first eclipse the Newman projection formula, then we are going to draw its corresponding Sohor's projection, and finally we will convert this into Fischer projection formula. One more concept is that whenever we interchange the groups of a particular chiral center odd number of times, its chirality reverses. However, if we interchange the groups of a particular chiral center even number of times, its chirality remains the same. Third and the final concept. If we reverse the chirality of all the chiral centers, we get the enantiomer of the compound unless the compound is a mesocompound. If however we reverse the chirality of some chiral centers but leave the others unchanged, then we get the diastereomer of the compound. As per step 1, we must eclipse this Newman projection formula. For that, notice that this is the front carbon and this is the back carbon. So, one way to eclipse this is to rotate the back carbon such that this methyl group comes just behind this hydrogen and this hydrogen just comes just behind this iodine and this hydroxyl group comes just behind this methyl group. So, I am doing just that. So, after rotating the back carbon, see this, I have kept the front carbon unchanged and I have rotated this so that this comes here, methyl groups comes here, hydrogen group comes here and hydroxyl group comes here. So this is the structure that I get after eclipsing the Newman projection. Now I will draw its corresponding Sohor's projection formula. So it is not that difficult to draw the Sohor's projection formula. It will be something like this. Then CH3 H and OH. You can easily verify that when we look at the Sohor's projection formula from this side, that whenever we look at this angle, we get the Newman projection formula. See, this is exactly the same thing that we are getting here. Now what we will do is we will draw the Fischer projection formula. For that, we know that in a Fischer projection formula, the atoms that are in the horizontal line are above the plane and the atoms that are in the vertical line are below the plane. In this Sohor's projection formula, you can clearly see that if we consider a plane like this, that is passing through these carbon atoms, these two groups will be above this plane and this group will be below this plane. So we are clearly getting the Fischer projection. Hydrogen and iodine, these two groups are above the plane and methyl group is below the plane. Similarly for here, these two groups are above the plane and this group is below the plane. So this is the equivalent Fischer formula for this Newman projection formula. Now we will compare it with the options. So you can see that for option number A, the chirality of this carbon atom is essentially the same because the positioning of the groups have not changed. So the chirality of this carbon atom remains the same here. Whereas for this carbon atom, notice that if I put the OH group here and OH group comes here and methyl group is then hydrogen will be here. If the OH comes here, then hydrogen will go here, and then I am again bringing the methyl group to this position. So methyl comes here, hydrogen will go to this position. So see, we are performing two interchanges and 2 is the even number. So since we are performing even number of interchanges, the chirality of this carbon atom also remains the same. So the chirality of both carbon atoms remains the same. So structure A is the same structure as compared to the original compound. It is the same structure. Now comparing for structure B, you can see that the same thing is written. So structure B is clearly the same, no need to verify. Now for structure C, you can see that for the front carbon atom the positioning is unchanged, so the groups are in the same position, the chirality is the same. But for the bottom carbon atom, notice that this iodine is coming here, and when the iodine comes here, hydrogen goes there, and these two hydrogen and methyl group is performing one interchange. So here also we are performing even number of interchanges with only one carbon atom, and the other carbon atom is also the same. So this carbon atom is the same, and since we are performing even number of interchanges with this carbon atom, the chirality of this carbon atom also remains the same. So this structure is also same, nothing is different between these two. As the three options A, B, C are eliminated, so the only option that is remaining is D. So D will be the correct answer. But still verifying, notice that the chirality of this carbon atom is the same because the groups are essentially the same, we are not changing it at all. And for this carbon atom, notice that what we are doing is we are interchanging the iodine and methyl group. So if we interchange this iodine and methyl group, then we get this configuration. So we are performing only one interchange, one is the odd number. Since we are performing odd number of interchange, the chirality reverses, and as per rule 3, this will be the diastereomer of the following compound. So option D is the correct answer for this question. Thank you for watching this video.